here's a neural model. As we take a look at these little parts of the neuron, let's get oriented first. Over here on this side would be the body, as well as we come down, this would be the distal portion, or the axon. So let's begin to focus on some of the structures that we can see here on the body. Well, first things first, we can kind of just say that that whole thing is the body, or also known as the soma. Soma means body, or also known as the perikaryon. So the perikaryon, people have defined it as, oh, that's the area around the nucleus, which would be the body. So that's why we call it that. So it could be the perikaryon or the soma. Most people call it the soma. If I were to lift this off, they're just trying to illustrate that, yes, it's three-dimensional, but if I were to cut this off, you can see that it looks very similar to a normal cell. You got the nucleus, you got all these endoplasmic reticulum with the Golgi body kind of here hanging out, and then all these little red dots, those are all the ribosomes, making all our wonderful proteins. So let's kind of get a couple things under our belt before we move on. If we broke out the neuron into four major parts, you can divide them into the things that come off the body, which are called dendrites, the body itself, the soma, or perikaryon, the axon that goes all the way down, and then the part that we actually don't see is when the axon then splits off into its axonal terminals or synaptic terminals or boutons, things like that, whatever you want to call it. But that part is not on this model. We have these three: dendrites, soma, and then the axon. Alright, let's take a look at some of the other additional structures that connect this. If a neuron is in space, it is useless. I mean, neurons are made to carry information, and it's just like saying if I have like a video cable or a computer cable and it's just sitting on my desk, it doesn't connect to a computer, it doesn't connect to a TV, it doesn't connect to anything, it's useless. So any kind of neuron has to be connected to something else, whether it's a muscle, whether it's the brain, or something it has to be connected. And here is demonstrated with plenty of other connections. So you can kind of see these other little things that hang off, and touching these dendrites are from other neurons, making connections, passing information. So these are our axonal terminals or synaptic terminals, and then in between would be our synapse. Synapse is just space between the cells. Alright, let's get to the nitty-gritty of the anatomy here. So if we already got the dendrites, the soma, the axon, well, what else can we see? We can see the nucleus, the Golgi body, and then this rough endoplasmic reticulum. These are called Nissl bodies. When somebody kind of looked at it, they saw, wow, there's so many kind of ribosomes hanging out from there. Well, that person was Mr. Nissl, and he says, they're my bodies, so I would call them Nissl bodies. I don't know if he had that accent or not, but regardless, that is Nissl bodies, like the stuff that you can kind of see on a microscope. They look like that. They're the ribosomes with the endoplasmic reticulum kind of hanging out from there. So, in addition to that, all these dendrites come together in the soma, and then there's only one axon coming out. So this part right here, you can kind of see it cut away, leading into this very, very long axon. This would be considered this triangle portion called the axon hillock, or the beginning of the axon. Beginning of the axon is the axon hillock, most sensitive part of the neuron. Specifically, when we say sensitives, it just has the most channels, so that things can be stimulated there, and voila, you can stimulate the action potential all the way down. From there, you can kind of see the axon coming down, down, with the axonal fibrils coming through there. So, but if you notice, this is not just the axon, there's some cells that surround the axon with its cell membrane. Well, these types of cells, their name is called neurolemmacytes. A lot of people call them now Schwann cells because Mr. Schwann actually discovered them, and from there he called them Schwann cells. So Schwann cells is a lot easier to say than neurolemmacytes, but regardless, that is what they are, neurolemmacytes, and they create what we call a myelin sheath. And the myelin sheath is all these little, if you can kind of see all these little kind of ridges and all these extra amounts of cell membranes, like so many of them. This is the myelin sheath. And some people can get confused. You know, when I point to this, is it a cell? Is it the myelin sheath? Well, I make this analogy. If you know of a character that wraps his arms around somebody, that just kind of wraps and wraps and wraps and wraps, I could point to this and say, what is this covering? And you would look at it and you'd be like, well, if it's a person, well, that's his arms. And then I say, well, who is that? Well, then you would say, well, that's that person's name. So in the same sense, if I pointed this, what's this covering, all these little layers, you would say that's the myelin sheath. But if I said, what cell is that? You would say, oh, that's a Schwann cell. Mr. Schwann cell, hello. So that is the difference between the myelin sheath, which is actually the layers of the plasma membrane of the myelin sheath. You can't separate them. Just like if I said, oh, So are you talking about his arms or him? They're the same thing. I can't separate them because they're attached and they're part of each other. And that's what we find here. This is a Schwann cell with the myelin sheath on it. And then as it comes over, you can kind of see Schwann cells are kind of short so that they have these little gaps. This is what we call the node Ranvier. French Mr. Ranvier kind of found these where there's gaps in between. And you'll also find they're also called neurofibril gaps or neurofibril nodes. So these are the nodes of Ranvier. And then lastly is this connective tissue covering, and this should extend all the way, but they kind of cut it off the rest. This is called the endoneurium. Connective tissue, it sounds a lot like endomysium if you think of muscles, but this is endoneurium, connective tissue sheath to give it some strength and stuff like that for the actual axon. So let's review really quickly. So this is our neuron. We have 4 major parts to it, and the parts of the neuron itself is the dendrites, the soma or perikaryon, and then the axon, and then the axonal terminals, which you can kind of see here from this other side. From there, you can see the perikaryon also has these nissl bodies as all these, ribosomal endoplasmic reticulum. When it blends into the axon, this is the axon hillock, and then the axon is surrounded by a myelin sheath, which is the cell membrane of a cell called the Schwann cell, and then you have multiple of them, so you have gaps in between called the nodes of Ranvier or neurofibril nodes, and then you have a connective tissue covering called the endoneurium. Here we are with the cross-sectional anatomy of the spinal cord. And one of the first things that we have to do is figure out what's anterior, posterior, lateral, medial. You can imagine that this is the anterior side and this is the posterior side. Here's the lateral side, and then of course in the middle, median, this is the deep center part of it. You can imagine that, why do we try to start off with that? Well, especially with spinal cord, it is imperative that you know what's anterior and posterior, also known as ventral and dorsal. So you may hear me go back and forth, but they're synonymous. Ventral is anterior, dorsal is posterior. But part of the reason why is because things are named anterior and posterior, and they are specifically, functionally, and anatomically different, and so you would get it wrong on the examination. So keep in mind, that's the first thing you should ever do when you step up to a spinal cord model or try to figure out anterior and posterior. Let me give you some hints. The first one is this big, gigantic, gaping kind of cleavage furrow in the front in comparison to this little crack in the back. And this would be the anterior median fissure, much deeper, wider, in comparison to the smaller posterior median sulcus, which is a little bit tinier. And that's one of the first ways that I would look at it. You can see this on a slide. You'll find a little bigger gap or a smaller one. Now you know that this side would be anterior or ventral. If, say, for instance, you can't see it, then I go to my second kind of go-to tell, and that is the horns. The gray matter is arranged in like this butterfly, and so the anterior horn, for some reason, doesn't go to the outer portion of this white matter. As you can see, white matter, of course, is axons. Gray matter is cell bodies. And so this collection, the way that we arrange it is the cell bodies stay and hang out just like right here, while all the axons continue out this way. On the ventral horn, or the anterior gray horn, and that's what this is called, it never touches the edge. In comparison, if you follow way back here, you'll notice that the posterior or the dorsal gray horn does kind of touch the border of the posterior side. So I always think, oh, horns go all the way to the back. And so that's the second way to tell. But say, for instance, you can't really see, it's kind of hard to see, the stain is off. How can I get one more chance? Well, you can actually follow the roots here. So these are roots that come off of the spinal cord. So this would be the ventral or anterior root, motor only. And then this is the posterior or dorsal root, sensory only, and then you'll see that the dorsal root swells to this gigantic, huge kind of swelling. We call swellings ganglions, and so this is a ganglion here, right on the dorsal root, so we call it the dorsal root ganglion, also known as the posterior root ganglion. It's just a collection of cell bodies because those sensory fibers are pseudo-unipolar, so all the cell bodies get conglomerated in here, and they make things swell. Please keep that in mind that every little bit of this is created by neurons. Every little bit. And so if you have less neurons, well, it's going to get smaller. If you have more neurons, it's going to get bigger. If you have cell bodies, it's going to, of course, get thicker. And so that's what we find as the posterior root ganglion or dorsal root ganglion. So if you have those three, you already know that this is anterior and posterior, and then this is lateral, and everything then falls kind of in step as long as you know what they are. So you already know anterior median fissure, posterior median sulcus, anterior gray horn, posterior gray horn. When they come together, they're called the gray commissure, and then of course the little central canal or central hole in there is called the central canal. The white matter, this is the posterior white column, this is the anterior white column, and then this would be the lateral white column. And you can imagine, oh, they're all named according to directional terms. Yes, and yes, and yes. And so then we still have the ventral root, or in the dorsal root, with the dorsal root ganglion. When they join together and they kind of fuse, you can see this over here, they become the mixed spinal nerve. When the mixed spinal nerve then splits, you get the posterior ramus and then the anterior ramus, or also known as the dorsal ramus, and the ventral ramus, and both of these just mean branch, and so it's a branch off of this the mixed spinal nerve. These are mixed, both carrying both motor and sensory, same with like the mixed spinal nerve, motor and sensory. They just go in different locations. So the ventral goes to the anterior side of the body, the posterior goes to that little strip in the back of your body. And so let's review. So if I were to be here, you could see this is the anterior median fissure, this is the posterior median sulcus, this is the anterior gray horn, this is the posterior gray horn with the gray commissure touching and making these guys connect. Central canal with the posterior white column in the posterior side, the ventral white column or the anterior white column on the anterior side, and then the lateral white columns on the side. They give off roots, the anterior root, the posterior root. The posterior root has a ganglion, so this is the posterior root ganglion or the dorsal root ganglion. They join together, they turn into mixed spinal nerve, and then they become the anterior or ventral ramus, and then the posterior or the dorsal ramus. You can see all these patterns be very similar in a second model. If I were to just step over here, notice you can identify everything. They look very, very pattern-like. This is a little bit more characterized. As you can see, this is, of course, the anterior gray horn, the posterior gray horn. This is the ventral root. This is the dorsal root with the dorsal root ganglion, a little swelling here, and then when they join, this becomes the mixed spinal nerve. One more shot, you can be able to see these guys branch off. You can see here, same kind of pattern. There's the gigantic anterior median fissure, posterior median sulcus. You can see then the anterior gray horn, posterior gray horn. This one does have the intermedial lateral gray horn, so it's something unique found in the thoracic region up to L2. And then you get the ventral root, dorsal root ganglion joins with the mixed spinal nerve here, and then of course the dorsal ramus is the guy that pops out here. This is the ventral ramus coming off of here. One clear exception is only in the areas of the thoracic you get these two little rami communicans, and that's something with autonomic nerve fibers. You get a gray and a white rami communicans, these tiny little guys that come off of the mixed spinal nerve. You can see it kind of here in the cervical region, but you only have a gray rami communicans coming off of this guy here. And just know that it's mainly for autonomic functions. There are neurons that carry autonomic innervation. Otherwise, everything is fairly unremarkable. You can still see the coverings on this. You can see the dura mater all the way here with the arachnoid kind of fused, with this space being the arachnoid, subarachnoid space, filled with cerebral spinal fluid, and then the covering over the actual spinal cord, that's the pia mater. You can see the dural root sleeves that kind of live on the actual spinal nerve and just kind of wrap around them and then protect it from leaking CSF. And that is the spinal cord. Here we are with the gross structures of the spinal cord, and this tends to be very simple because there's not too many structures that can be kind of clearly identified, or just that there's just not. So let's of course get oriented, of course, as at the beginning. So up here is the brain, so this is the most superior aspect. Down here would be the most inferior aspect. This part up here that I'm touching would be the anterior side. Behind this would be the posterior side. First things first, we kind of see the length of the spinal cord is run by the anterior median fissure, this little crack that races all the way straight down. But one of the other things that we see is that the spinal cord is not like consistently thick all the way across. You get two thickenings or enlargements here and down here. This would be the cervical enlargement. You can see it gives innervation to the upper extremity. And then the lumbosacral enlargement, which gives, of course, the branches of the lumbar plexus and the sacral plexus. So those are going to innervate our lower extremities. So that's the first two things that we see, the cervical enlargement and then the lumbosacral enlargement. And then, of course, right at the end, you see the spinal cord actually end, strangely, at L1, right around L1. If this is, of course, T12 because of the ribs, and then you get L1 right at the end. It ends like a cone, and the cone is called the conus medullare. medullaris, or also known as the medullary cone. So conus medullaris or medullary cone, both are acceptable. But yet off of that comes off this tiny little itty bitty strip that comes off. Well, this is the filum terminale. It's actually pia mater. I always think of my sister and grabbing her foot with her sock on and pulling her sock off, and then it's just the sock still attached to her foot. And that's what the filum terminale is, just pia mater that's like stretched all the way. It acts like an anchor. It goes all the way to the coccyx, gets anchored down so that the spinal cord doesn't bounce around too much. But if the spinal cord ends at L1, of course you have to have innervation below that. You can kind of see all this. So how do we do that if the spinal cord ends here? Well, we get this large collection of rootlets, anterior and posterior rootlets, and this is what we call the cauda equina. Literally translated as the tail of the horse. Cauda, tail, and equina, horse. But don't call it that. Don't call it the horse's tail. Call it the cauda equina. So this is the collection of rootlets here. And so let's go through again. This would be the cervical enlargement. This would be the lumbosacral enlargement. This would be the anterior median fissure. Crack all the way straight down. This would be the conus medullaris at the end. This would be the filum terminale that comes off of that, made out of pia mater, anchoring itself to the coccyx. And then all these rootlets is the cauda equina.